Good evening. Yeah, Mr. Joshua, Charlie, is the meeting open or it is a closed one? Is Joshua here?
Yeah, hello, sir.
Can I be heard? Oh yeah, Joshua.
Yeah, please, it's open.
Oh, okay, I see. Hang on, I'm coming in.
You there? Let me say.
Yeah, Joshua, I was asking if the meeting was an open or closed one. Please say you can speak now.
Please, it's open. It's all.
Oh, okay, okay. And please send out alerts and then when then yeah, some of our people were asking about this there. So
Sure, sure, sure.
people will start in about a minute or two. Okay, just allow.
Yeah, hello, Mr. Wilson.
Yes,
Please, can you
it's
tag
done.
all of them? Yeah, please, can you tag all of them? I'm not an admin in some of the groups.
Okay, okay, that's Okay, so at this point, I believe all those who will join have probably joined. And then let's not waste the time of those who have joined. Let me move some of these folders off of my screen before I start sharing. Okay, there's quite a few things. Uh, okay, so I forgot this. So the assignment file itself, Charlie. Come, let me open the questions as well. Okay, I'll stop sharing because I have to go to my second. Right. Okay. Good evening once again. I believe you can share see my screen. Yes, if you can, that's good. You may react with a thumbs up or something, but I believe you can. And here's a quick recap of what we did the last time. Those who just joined, I advise and every single one of you that today will be the last time we'll be discussing this, right? So I want you to try to follow with your machine ready. And when we get to a point after you have written your code, you take your screenshots immediately, you paste, and then you follow. Or you ready it down for when you are actually compiling your file. Is that clear? All right. So let's do a walkthrough of what we discussed the last time. The assignment says that we are going to need to use the Littleman computer, specifically the Higginson's model, this one here. So that's what we are going to use. And then we are also going to use the Central Processing Unit Operating System Simulator that was given to us in the class. All right. The first major activity was that we are to perform this controlled execution and then trace the program. We are to copy this program here and enter it into our Littleman computer. So we did exactly that in our last session. So we copied this and we pasted it into our Littleman computer. And we submitted. Upon submission, the code was accepted. Pacho, nipa na oyɛ saa adeɛ no, ɔngyae. Why? Ɔngyae. We've been joining meetings for a long time now, so we can't keep making the same mistakes. Right, let's proceed. After you load that code into your simulator, the step 2 says that you are to enter, you should run the code, and as you run the code, when you are asked for inputs, enter these two inputs, 7 as your first input and then -7 as your second input. And it also says that we should only step the program. It means we shouldn't, what do we call it? Run it fully. We should step it one by one and observe what happens at every stage. And as we step it to, we are to list what happens at every step. So the steps will be step 1, step 2 in your table, step 3, step 4, step 5, 6, 7, 8, 9. It says for at least 10 steps, so you can add one more row beneath it and then you step it 10 times. So add one more row and then step 10, like that. So the program counter values will be updating sequentially for most of the time, but later on it's going to branch. So you will check that later. And as for the instructions, they will be the ones that you have put into your RAM space, the assembly language code, the INP, ST, etc., etc. The opcode and address, we'll look at that as we go. Let's run our instructions. So let's step it first. So first reset the program. Step it once. So since you will be required to explain what happened here in your video that you will do, let's just talk about it. So the program counter first was updated, and then it went to tell the memory address register. So it gave the memory address register which address it was supposed to address. The memory address register communicates with the memory buffer register, and then the memory buffer register comes to take whatever is stored in that address. When it takes whatever is stored in that address, it is carried to the instruction register. The instruction register now, through the control unit, the control unit is able to break down the instruction that was stored inside the address into a separate opcode and then an address. So when it separates it into an opcode and an address, that's what you say is the decoding phase of the cycle. And after that it's done, the execution is completed. So it's complete execution. It means that that's what the code wants. So currently what we have done is we have decoded inputs. The input code was 901 and the code has separated it into 9, which stands for input, and 01, the address of where that input instruction was stored. So then the accumulator currently stands at 0. So we enter an input according to the question. The first input should be 7, right? Enter your 7. 7 is carried into the accumulator. Once it is loaded there, we step the program again to continue. So step program counter increments. It goes to the second address to go and take the instruction there, which is the store instruction. So then the second instruction says what? Store at 20. So it just did exactly that. So those who are lost because this is your first time, we have done this already. So we are just breezing through so that we can move on to the central processing unit operating system simulator. Then we step this again. After stepping it, retrieves the second input instruction and decodes it. And the question says that our second input should be what? -7. Now, I am doing this without filling my table, but as you work, you should be filling your table as well. It says after step 1, what did you see? So this is how you will fill it. The program counter at step 1 incremented to 0, 1. The instruction there was the input instruction, right? So you type it in INP. My P key doesn't work. So, you type in INP. The opcode and then the address there was 901. You can read it from here. So 901 from when we entered the first input, or you can read it from the address that holds the input, 901. So we write that 901. And then the accumulator before. So before the input was entered, the accumulator was 0. But after it was entered, the accumulator became what? 7. That was the first one. And which mailbox changed? At this particular stage, none of the new mailbox changed. So you can say none. And we stepped it again at step 2. The instruction then was store. It was store at 20. So you write that. And when that happened, the opcode and the address was what? 320. So 3 for the storage and then 20 for the address. And then the AC before that was 7, right? And then after the storage was done, the AC still remained 7 because no change was done to it. It was merely read. It was not written. And then at this point, there was a change to a particular mailbox. So when we stored at 20, you can see that all the mailboxes, they have not changed, except the ones that were initially holding the initial instructions we put in. The only one that has changed is the mailbox 20. And it has changed because we have stored the value with the accumulator at that particular location. Therefore, it has updated from 0 to 7. So which mailbox has changed? It is mailbox 20. Write that in. We have stepped this how many times? So let me see, input 1, 3. So at step 3, right, that's 0. The program counter incremented to 3. The the address was 901. Hold on. Hello, please, can I be heard? I'm sorry, a call came through. Can you hear me clearly? Respond, unmute and respond, please, if you can hear me. All right, thank you. So, all right, all right. Sorry if I'm moving too fast, but we don't have the time to be going through. And we've already tackled this, so we are just going over it. And I know those who have already done it, this is frustrating because you've already been through this. So let's move faster, even. So then at the input instruction, the opcode and address was 901. The accumulator before we inputted was 7. But after we inputted the second time, it changed from 7 to -7. And that's where we are standing now. So you put that there, -7 or -007, however you want to write it. And then which mailbox changed? None of the new mailbox changed at this step. So still NONE, none. And we step it once again. So let's step. After stepping, yes, yes, yes. It goes to pick the instruction on the fourth line, which is the add instruction that you see over here. So as I paste that instruction, it will read the value in address 20, combine it with the 7 that is stored in the accumulator. So -7 plus 7 gives us 0, right? So then we do that. So at program counter incremented to 4 at this step. The instruction there was add 20. And the opcode and the address at this particular step was what? 708. 120, sorry. and then the accumulator at that point before it was -7. After that was done, it became 0. Which of the mailboxes changed? None of them were affected. We keep running this code. So let's run to the next one. This is about where we will stop and move on to the next program to do. So it fetches the instruction at the next site. That was 708, which said to branch to address 08. And this is where the program ran into a problem. So at this point, the program counter that increments sequentially has changed from 3 instead of going to 4. Rather, it stands at what? 8. And that's a problem. We learned that the program counter increments sequentially to give the code an order to flow in. But we also learned that jump instructions or branch instructions force the program counter to move to a particular address. Then it starts the sequence from that address. This particular one says it should branch to address 8. However, if you study your code carefully, address well, the address 8 currently holds the instruction 8.0, and then 8.0 is not an instruction that can be executed in the normal sense. It is just a declaration that says in this particular address, we hold this particular data value. So for that reason, if we branch to address 8, there will be no execution. And even if there is an execution, remember, the program counter continues the sequence after it does the branch. It means from 8, it is going to continue to 9. From 9, it will continue to 10. The problem is if we move from 8, there is no address 9. It means address 9 just holds a bunch of zeros. And it will just continue to address 10. So address 11, address 12, address 13, address 14. It will never come by the halt instruction because halt comes before address 8. Therefore, the program is going to run endlessly. So this branch instruction made the code fail in this instance. So keep that in mind. So at step 5, the program counter incremented to 8. And then the instruction at that step was branch. It says branch if you find a 0. So it was BRC, the branch if 0. It says branch to address 8. And then the instruction there was what? 708. That's the branch instruction. And then the accumulator before that was 0. The accumulator after that was 0. And then which of the memory addresses changed? The answer was still none. If you continue the stepping, it says you step for 10 times and you observe what happened. If we step again, program counter now continues from 8 to the next instruction, which is 9, which still holds nothing, 0, right? So then when it goes to 9, program counter has increased to 9 like that. And then the instruction at 9, we don't know. So there is no instruction. You can say none. So there's no instruction there or no. And then the opcode and the address at this point is 000. And the accumulator before was 0, after 0, and the memory address that changed was none. That is going to keep repeating till your 10th step and even beyond. Because from 9, we go to 10, we have not given any instructions to those particular addresses. They are just a bunch of empty spaces. So we'll just be jumping empty box to empty box because we jumped to a point that was empty and a point that is far beyond the halt instruction. Therefore, the program is going to run endlessly. So now the questions that followed up said, at which step did the branch instruction execute? So the branch executed at step where? Step 5. This is the step, right? So at step 5, after the add instruction, that's where the branch executed. You stated nicely. Why did the program counter not increment normally at that step? So then the branch instruction overrode the program counter's sequence. It overrides the program counter sequential flow, forcing it to jump from address 4 all the way to address 8 and identify when memory was read. So memory was read when we were doing the add instruction. So during the add instruction, the program went straight to memory and retrieved the stored data, the 20, the 7 that was in 20. So during the add instruction, that's when the memory was read. You write that, or during add 20 or at step 4 during add 20. Identify when memory was written at the store instruction at step what? 2. So when we stored into memory, we wrote on the memory, we wrote into memory. In other words, we edited what memory was containing. So that is writing. Explain how this program demonstrates the von Neumann model. So according to the von Neumann model, we know that instructions and then data stored inside the same memory addresses. So that's the stored program concept. And as you can see, the instructions that we put in the code at first here, they are currently held inside these memory spaces, 0, 1, blah, 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 all the way to this side. And these same memory spaces are capable of storing data too. As you can see, it is currently holding a data value. So you can say that the data value 20, the data value 7 was held in address 20, alongside the instructions that were sequentially held in the first few addresses, 0, 1, 2, 3, 4, 5. This demonstrates the von Neumann concept, which says that programs, data and instruction are stored inside the same memory spaces. All right, that's the explanation for that. You phrase it neatly. Now it says we are going to modify the program. We said modify the program so that the system continuously accepts numbers. It stops only when the user enters 0 and it outputs the cumulative sum before halting. So then we are going to do it, create a loop, and it will take in the numbers and taking the number just does a 0, the program will stop. And it will also bring out the cumulative sum. So it brings out the sum of all the numbers that were entered by the user. And it has given a few restrictions. It says we must use the branch if 0 and the branch always instruction. And we must only use one memory location to store the data. And we must also demonstrate the looping clearly. So in our last, what do we call it, session, after much delegation, we came to a conclusion, right? And then there was that this edit to the instructions was the best to do. So we create a load instruction. So we first assign a data to memory address 20. So we make it like this, 20.0. What this means that 20 address 20 holds a data value, and that data value is 0. And then we first load address 20. So LDA, all caps, okay, the case sensitive LDA 20. And then after we load address 20, we take an input from the user. So loading 20 means copy what is in 20 and bring it up here. So that's the loading. Or move it, carry it to this side. And then what else? We take an input from the user because we're trying to add. So you write INP, right? My keyboard is right. Copy, that's good. So you write INP. The next instruction is add what the person has taken or the user has entered, add it to address 20. So if the input was 5, it will now be 5 plus the address 20, which is currently holding 0, right? And then there are some modifications that we have to make as well, because the program says in case the user enters an input that is 0, the program must stop. So this means under the input line, we have to put a condition that will stop the program if the user enters a 0. So we are going to put the branch instruction, the particular one, the one that says branch if there is a 0, the BRZ instruction, we put it over here. That way the program will branch in case of a 0. But we have to make sure it branches to the right place so that I will be able to display the cumulative sum that we're talking about at first. I will come to that later. So we'll add the address that it branches to later. So it says if it's 0 branch, but if it's not 0, add it to 20. So add the input to 20. After adding the input to 20, now let's store that inside 20. So we store the inputs in 20 so that the new data held in 20 will be updated. You understand? And when the program loops again, that updated value will now be the one that will be loaded. The next input will be added to it, and then it will be added to 20 and stored in 20, and then the looping continues like that. So we store that in 20. Let's carry the output instruction from here. After storing in 20, we are going to have to call 20 again, right? So let's bring outputs somewhere later. Let's bring it here. All right. So after storing 20, if we are going to use 20 again, then we have to call 20. So how do we call 20? We call 20 by loading 20. So LDA 20, like so. So then we are loading 20. And then after we load 20, the program says, fulfill this particular one, branch to 00, branch to 00, and then you are done. Have we skipped something? Yes, we have. The load 20 instruction, we have put it at the wrong spot, right? So when we store in 20, we branch 0, we load 20, and then we play. We have to put the second load instruction under the branch here. And then that is for good measure. And you'll see why in our next step. So now after we do this, we want the program to keep taking input from the user. But if the user enters an input that is 0, the program will now have to jump to a place where it will display the sum of what it has already added, right? And after it displays that sum, it stops. So what we are doing currently is we have put the set of instructions on this side so that after the user enters 0, the program will load what was held in 20. That will be the cumulative sum at that time. The out instruction will now display the cumulative sum. And then after it does that, the program will now halt. So it means you're going to have to make the program branch from this side, if there is a 0, all the way to this side. So that way, the value that was stored in 20, after it has been loaded, it will be displayed, or it will be copied to this side. It will be outputted, and finally the program will stop. So what address would this be? This is 0, 1, 2, 3, 4. This is 5, 6, 7, 8. So this is address number 6. So branch to address number 6, like that. So let's submit that. And now our program has been successfully edited. So let's see if this program is able to meet the requirements of the question. There were some things that you were supposed to do. Required evidence. It says you take a required evidence and you submit a screenshot before execution. So currently we have our program. We've not executed yet. You can take your first screenshot of it. I don't advise you to take a screenshot of mine because this account here, I don't know if the lecturer is going to be very, if he's going to check it carefully, but if he does, he will see this. I have a few tabs here: Wayground, risk teaching, and all these ones. But if you can take a screenshot and you edit them out, yeah, you're cool, you're cool. Because in the end, I think this might be the only way to do this particular loading using one memory address. If we're allowed to use more, then there will be several ways to do it. But while using one memory address, we can do a few tweaks here and there, but this is the best way to do it. So take the screenshot before execution. You take a screenshot during the loop. So the loop will be happening somewhere here, branch 00. So as that loop is happening, the program counter value is going to update and change back to 0. So I advise you to take a shot of when the program counter reached 04. And then after you run that again, you take another shot of when the program counter changed from 04 into 0, 0, instead of it going to 05 or 06. Is that clear? So it goes to 05 and then it jumps to 00. That's the idea. So you are going to take a shot of those two to show that the loop was happening. And after you do that, it says after you have run the program all the way to the stop, after it halts, you show another screenshot at termination. Is that clear? And then after you show that screenshot, you give an explanation of how the program counter was behaving during the loop. So then your answer to that is going to be that during the loop, the program counter broke its sequence and then jumped, or it was overwritten and then it went to 00 and it's moved sequentially. The accumulator, okay, let's just run the program and then you can tell. So we reset a step. After stepping, program reads the instruction. First instruction says load the value at address 20. So it is going to read what is in address 20, which is 0, and it will read that and carry it to the accumulator so that it can await a mathematical or a logical operation. If we step it the second time, it takes an input from the user. So instruction 901, which is interpreted or decoded as input. So we give it an input. So let's give it a multiple of a number so that we can easily see the accumulation happening. So I'll give it 10. I hit enter. 10 is now stored inside memory, the accumulator. And then after it is stored in the accumulator, if we step it again, so it says we've given it the input 10. It says add it to 20. So it is going to read the value in 20. So we read the instruction first, sorry. step it again. It reads the instruction, and it comes back to read the value in 20 and takes it to there. So it's reading the value in 20 now. Oh, this is too slow. It carries it to the accumulator, combines 10 with the initial 0, right? So from here on, I'm going to be running it fast, okay? You will do the running and then we take it. So remember to take your screenshots at the right places. You step it again. It now stores the value in 20. And then we step it again. The program will now branch back to 0, 0. So then program counter is now updated to 0, 0. So this is the program counter behavior that we're asking you about. So we step again. Input, it loads 20, sorry. Takes an input from the user. The inputs that we are going to enter will be 10 again so that we can see the build up happening. So if I enter another 10, now it's stored in the accumulator. If I start the program, it runs quickly, retrieves the data, takes the 10 that has been stored in 20 now and combines it with my second 10, and then it becomes the new value. If I step it again, I add a 10, same situation will happen. So it will keep happening until I enter a 0. And the 0 will only affect the branch 0 instruction. All right, so then let's add another input. This time I add a 0. Once I enter a 0 and I step the program, let's see what happens after it finishes running. All right, so what has it done here? The program has now taken the sum in the accumulator and it has outputted it. And if I step it again, the program is going to halt. Right. Right. So now let's see what has happened here. From the start of the program loads the data that I stored in 20, and we initialize that to be 0. So it loads the 0 and it stores it. It brings it to the top of the code, the instruction. Then we take an input from the user. If we take an input from the user, then we check the condition that says if it is 0, jump to address 6. And when you jump to address 6, load whatever is stored in 20, and then display it with the output and stop. If it is not a 0 on the other hand, add it to 20. Store it in 20 again. Branch to 0, 0. So branch always to 0, 0 means jump back to this side and repeat. So it will take an input. If the input is 0, it will stop and come to address 6 and continue from there. But if it's not 0, it adds it to 20. It stores it in 20. It branches to 0. It loads 20. It gives an output. It halts. And then it keeps going on and on. Once we enter a 0 on the other hand, the branch if 0 instruction executes. And when that instruction executes, it jumps to this side. It loads what we have stored in our accumulator, the cumulative sum that was stored in 20. It loads it. And after it loads that, it moves on to the next line, out, it displays it, moves on to the next line, halt, then it stops. So that is pretty much it for this side. So you put, after your program halts, the last screenshot into your file as well. That's the one termination. And you explain the PC behavior during the loop. And you also explain the accumulator update. So you can see that the accumulator's value increased by the numbers we were adding at every single loop or after every single loop. And the memory usage, it was only memory address 20 that was being used. However, the memory address 20 was being updated at every step. So when we enter a 5, it updates to 5. When we enter a 6, it becomes 6 plus 5, and then 6 plus 5 becomes 11. It's stored in 20. So then you can also say that the memory was constantly being read and written during runtime. That's another behavior of memory that was demonstrated. All right. But C says we should count the total number of instructions executed before the program halts. And with this one, with what we did, let's count. We entered two non-zero outputs, that was 10 and 10. And we also entered two non-zero inputs, sorry, that was 10 and 10. And we also entered 1 0 inputs, that was 0 itself. The two non-zero inputs use a different set of instructions, and the 0 inputs also use a different set of instructions. Them together. Let's see, I entered a non-zero input. So when I entered 10 the first time, I use this line, that's 1, 2, 3. Okay, no. When I entered 10 the first time, I use 1, 2, 3, that's here, 4, that's here, and then 5. That's when I entered 10. So it uses one line, this line. It doesn't use the branch line. It uses the add, the store, and then the branch always. That's 5 instructions. We did that for two numbers, 10 and another 10. So that will be 5 extra instructions, making 10. And when we entered 0, what happened? We loaded it all right. When we took the input, that was 0. So that's 2. And we branched to 6. That's 3. So we continue from 6. That's 4. We output, that's 5. We halt, that's 6. So then there are 6 instructions in the 0 inputs, and there were 5 in the non-zero inputs. Putting that together brings you towards 5 plus 5 plus 6, that is 15. But it says before the halt instruction, right? So it means you can ignore the halt. So you're going to even have 5 plus 5 plus 5 because you're ignoring the halt. That makes 15 instructions. So you write that the total number of instructions executed before the program halts was 15. You can choose to explain if you want. If each instruction takes 1 clock cycle, compute execution time at 1 megahertz. And we know that the formula for that is CPI, that's the count cycles per instruction times the number of instructions divided by the number of, or the rates here, that's the megahertz. So in our case, 1 clock cycle means 1 is the CPI, so 1 times the total number of instructions, which is 15, divided by the rates, 1 megahertz, which is equivalent to 1 million. And then after you divide that, the execution time will be given in seconds. So 1 times 15 divided by 1 million for the first one. The second one is 1 times 15 divided by 1 megahertz is 1 million seconds, and then 2 megahertz is going to be 2 million seconds, right? So then you divide by 2 megahertz in the second question. So it will be 1 times 15 over 1 for the 1 million for the 1 megahertz, and 1 times 15 over 2 million for the 2 megahertz. Third question says if the CPI changes from and then now becomes 2, recompute execution time. So I said it's a CPI times CI, that's the instruction count IC, divided by the rates. So it will become 2 times 15 divided by 1 million. That will be 30 over 1 million, and then you convert it to a decimal if you want to. And you write your answer in seconds or microseconds. And then that's for 1 megahertz. If we do the same thing, 2 instructions per cycle, and then you what do we call it? 2 megahertz. That's going to be 2 times 30 divided by 2 million. And then, you move on from there. Explain why the Littleman computer does not demonstrate pipelining. Pipelining is a concept in architecture of CPUs that makes the central processing unit able to process or execute different lines of instructions at the same time, so simultaneously. Now, the Littleman computers we have observed can only execute one instruction at a time, strictly one at a time in a fixed sequence, unless, of course, there is a branch or a jump instruction, but still, that also happens one at a time. Therefore, it does not demonstrate pipelining. So unlike a normal CPU, which is able to run different tasks simultaneously, the Littleman computer strictly runs one instruction at a time. Therefore, it does not demonstrate pipelining. Identify one limitation of the von Neumann architecture observed in this experiment. That limitation was what happened in the first lines of instruction when we branched to address 8. due to the fact that data and then instructions are held in the same space, a little wrong addressing can lead your whole program to go awry. So you can say that von Neumann bottleneck that was encountered was the stored program concept. Due to this very concept, if data is wrongly addressed, then we might end up addressing or reading an instruction instead of data, and this will lead to inconsistencies in the expected, display or output display. Wow, the recap took too long, but we will finish this thing today, amen. We'll finish it. Let's move on. Major activity 2. So let's switch from our little man computer. Let's open our central processing unit operating system simulator. So to those who have been in the lessons and those who are members of the makeup class, I believe you already are familiar with how to add instructions to the central processing operating units simulator operating system. However, those who are new to it, you are the problem right now. You are the ones who are going to waste that time. It's in here, say, don't just canon I'm enjoying it. But I'm open free. Okay, let's proceed. So it says register tracking. We have to load a simple add program into the central processing unit simulator. And we should step through execution and complete the table below for at least 6 instruction cycles. What this means is that the instructions you're coming to write should have at least 6 different lines of instruction to complete those 6 instruction cycles. And then through that, we complete the table by writing the instruction here, storing the program counter value, recording the instruction register value, the memory address register, the memory data or memory buffer register, the accumulator, and there is no accumulator in this one too. And then we have to outline the action performed. So a little something to add to you. The central processing unit has an arithmetic logic unit, and the arithmetic logic unit is what the accumulator mirrors, a part of it, basically. When we are using the central process, the CPU OS, when we are using that, the accumulator's job is done by the registers themselves. So when the data value is being worked upon, the registers will hold that value. When the data is summed with another data, it is held in a destination register. When there's a subtraction, it is held in a destination register. So you'll be using what is happening inside those destination registers to update your accumulator here. It says you must provide screenshots clearly showing your program counter changes. So you can take a particular instruction execution, not for all of it, and then you will show how your program counter updated from 0 to 1. Instruction register contents. Your memory address register holding memory addresses, memory buffer register holding data, accumulator updating. For the accumulator updating, we can't provide, but at least we can talk about the destination register. What's the situation? Right, so in order to do this, it says we have to add a simple add program to our software. So let's load an add program. Everybody go to the bottom left corner of your screen, where it says program name. Type the name of your program, the program you would like to add. So let's just use a random name. Set the base address for the program. The base address is where execution starts from. Unlike our, explaining all this will take a lot of time. Unlike our LMC, this one, the program doesn't just start from 0 always. It tries to avoid the conflicts of the store data concept. So it always starts execution at a particular base address. What this means is that every single line before their address will never be used inside your explicitly stored codes. However, they will be used for things that the CPU will be running internally to execute your instructions for you. So the base address can be any number. Let's use 200. Last time we used 100. So today let's use 200. And after you do that, hit add. And after you add, come to this place where it says base address, untick this blue checkbox, and then write the base address that you set into that space again, 200. And after you do that, you can save the program. So when you save the program, so you can save it amongst all the other ones you have done. So save. When you save the program, you realize that it is now recorded amongst the programs in the program list. Panku with the base address 200, starting at 0, and then the type is the register program. All right. So let me remove all these bubbles from here. All right. So after doing this, we can now add instructions to our program. I'm not going to explain how that is done because we have covered that in 2 lessons before. It's too bad, actually. There's no time. Adding a new instruction, the program said we should add a simple add instruction. And we know that in the CPU OS simulator, it's when you do instructions like load bytes or load word or load, etc., they do not load from registers, but they try to load from memory. And that brings a lot of problems. So we use the move instruction instead to carry data around inside this program. So we are going to use the move instruction here. I'm going to move a particular data value. So let's say we want to add 2 numbers. We want to add the number 15. So we are moving the value 15. We are carrying it to a particular register to hold it there. So let's store 15 inside address, let's say address 7. So we are storing 15 in address 7. And you hit new instruction, and it is added over here as your instruction in RAM. That's the first one. And so now it means we have stored the data value 15 inside address 7. So you can come here and then state these things here. But we have not yet run the program, so when we get there, you'll see. And then the next one, we need to move another data value. Since we are trying to sum up 2 numbers, we need to move another data value into there. So we can move another value. This time, let's move 15 plus maybe 10. That's easy to follow, right? We move that to another register, and you realize the way it says destination operand here, that destination is going to be where the end results of whatever you do will be stored. So you start at a certain point, you end somewhere. That's the destination. So currently we are also moving 10 to register. We use register 7. Let's use register maybe 12. Okay. And new instruction. So now I have moved 15 to 7, then an immediate data value, and I've moved 10 to 12. After we move this, it says an add instruction. So you come to the arithmetic column, you select an arithmetic operation since we are adding, and then we are adding what is stored in register 7 to what is stored in register 12. And we are storing that in register 12 again. So you take what is in register 7, R07, you add it to what is stored in register 12. And then since register 12 is still the destination operand, it will store in register 12. It will be stored in register 12 again. So 2 and 2. Now, since it says that we should do it for how many instruction cycles? 6 instruction cycles. We need to add some fill-in codes. And add some fill-in codes that will help us, increase the length of our program. So let's use sum. We can use a jump instruction. We can jump to a particular line of code, but that will create a loop. So let's not use that. Let's use a push instruction. You know that the push instruction pushes data into RAM, right? So let's use a push instruction. Before we push, let's do one last move. We just want more numbers. So currently we know that there is a value held in register 12 after we add. So why not remove that value from register 12 and move it to a higher register, like maybe register 20, just to add more lines to our code. Yeah, that's 4. We can now add another line that pushes the value at register 12 into the memory with the push instruction that we learned the last time we met. So push the value in register 20 into memory. So new instruction. And then finally, we can add the halt line so that the program does not run indefinitely. So we go to control transfer, last halt. If you want to understand how or what is happening right now and you're confused, we will later provide the link to our YouTube page. You can go and watch the fundamentals that we gave concerning this program. And after you do that, perhaps you understand what is happening. So I am on joining make that's okay. I'm doing advert. Right. So now we've added 6 lines of code. There is line 1. The job of line is to move the number 15 into the register 7. The job of this is to move 10 into register 12, add register 7's value to register 12, move what is stored in register 12 after the addition to register 20, and then push that value into the RAM. So currently this will be held in the registers, but the push instruction is used to add into the RAM. And then there is the halt instruction. And it says, as we are doing that, we have to observe a few things. It says that we should observe the behavior of the PC and then the IR and etc. This is the IR, the instruction register. This is the program counter. This is the status register. That will flag negatives and then overflows and then, zeros. And then there is the stack pointer. And the job of the stack pointer is to always point to the top of the stack. So it always points to the thing that stands on top of the RAM. So the thing that is at the highest of the RAM, it is always held. The stack pointer holds its address in the RAM. And then there is the base register that holds the base address that we entered to be what? 0. And there is the memory address register. Memory address register always holds the address of the current data being executed, the address. And then we have the memory data register, which takes the data that is inside the address to be executed, or which reads and writes data into the current address that we are working on. It's also known as the MBR, memory buffer register. Okay, you have your registers on these sides, and these registers are the main registers, the general purpose registers. So these are general. These ones are also registers, by the way, but they are the CPU registers. And these are the general purpose registers that will be holding data and then moving them quickly to the CPU so that runtime is shorter. When we do these things, according to what our codes have said, when we run the first line or we step the first line, we should see memory address 7 updates with the value 15. So look out for that. And then when we do the second one, we should see memory address 12 updates with the value 10. And then when we add RO7 to RO12, it will be stored in RO12. So we should see address 12 updated with the value 10 plus 15, which will be 25. That's address register 12 here. And then when we are done, line here says push R20. So push R20 means take what is stored in register 20 and come and bring it into the memory. So you see the stack, the RAM here. It will now be updated with what is held there at address 20. And finally, it says halt. So we are going to first reset the program. So always reset your program so that it moves to the very first line and you'll not end up executing from a region where you didn't intend to. Let me hide this. All right. So reset program. The program has been resetted. We're on the first line. And now it says we step. So when we step it once, the instruction at that side was what? Move immediate value 15 into RO7. So you are going to write exactly what you see here inside your instruction column. Okay, so it says move immediate value 15. Where's the hash key? All right, so move immediate value 15 to register 7. So RO7. You do that for the first one. And then you update it with what is held in the program counter. So the program counter is now holding 6. And that is for a reason that I have explained in earlier lessons that I'm not going to explain today because time and call. And then the instruction register is holding the current instruction that you're executing, which is move 15 to register 7. So you repeat that same instruction inside your instruction register. So you have to expand your table to fit all of those things. So copy and paste. Life is simple. Okay, you get the idea. Expand your table, okay? Expand your table. Expand. Expand everything. All right, let's just move. Memory address register is currently standing at address 200, so you write that into the memory address register space. Expand the table properly, or don't do what I've done. In mine, I have expanded it properly, so you do same. And the memory data register, the memory buffer register is holding the same instruction. The data is that we are moving. So the instruction is a set of codes, right? Just like when you were looking at it in the CPU, you see the instruction is a set of codes. When it is from memory, it goes into the memory data register still. So the same instruction, move 15 to register 7. And then the accumulator, which is register 7, currently holds the value of 15. You see that? So then I said the registers will now act like your accumulators. So then where it says accumulator, we hold 15. You write that there. And the action performed. The action performed is move immediate value. So immediate value are data values like this one. So move immediate value. What's the value? 15 to register 7 or to R07 like that. So it moves it. We come to the next line. So for then, please, I have outlined what this one is. So you are going to do the rest yourself. I'll be telling you what the actions are so that you'll fill them in. Time is fast spent. I'm here to guide.
I want
We
to ask
step
a
it a
question.
second time. Oh yeah, sorry, go ahead. And then please keep it fast, okay? Yeah, I'm listening.
I see that your first input, the PC is 6. Why is it not 0?
Why is it not
0.
0? So I surmise that you are not a member of the makeup class, right? That's why I'm saying that these things, we have already treated them. And the makeup members, we've treated this particular CPU simulator lesson 2 times. So questions like this will draw us back. But let me just go ahead and answer you. You see, the Little Man computer, it is a it's a far cry from what the CPU actually is like. It merely tries to make you understand it, but it doesn't do it justice. The CPU uses sequences to execute the data that it is running on, or the instructions. However, each data is stored in a different number of register spaces, because each, not even data, each instruction has a different size. For example, the move instruction here has a size of 6 bits. So it means the instruction here is stored in 6 separate spaces in memory. Therefore, all the data spaces from 0, 1, 2, 3, 4, 5 are all the way to 6 are holding the move instruction. You understand? It has been spread in all those data spaces. So for that reason, we will not move from 0 to 1 and then from 1 to 2. Because if we move from 0 to 1, then you're technically saying that, okay, then the move instruction was only stored in 1 bit. But no, the CPU will store the move instruction in 6 bits. You can realize that when the second move instruction was entered, the next instruction was at address 12. This means that another 6 bits was used to store the move instruction. Now look at the increments on this side. I'm talking about where it says the logical address, okay? The increment on this side was from 12 all the way to 17 after the add instruction was added. So what does this tell you? The add instruction was stored in 5 bits. Therefore, the increments changed in sequence to this. It's still a sequential flow, just that the numbers change or they vary depending on the size of the current instruction we are holding. So the value here is now at 17. So yes, it is trying to move the program in sequence by jumping to the next address, or the address of the next instruction. The next instruction is currently being held in 17 because all of the previous spaces are being used to hold the add instruction. So is that clear?
Yeah, I get you. Thank you.
Yes. So please, the Little Man computer does not do this because it doesn't show you how the data, each one is stored with a different size. It only tries to mirror their functions, but it doesn't mirror it well. Thank you for that question. It threw us back, but still, thank you. Someone got something. Let's proceed. What step were we on? Did we step it a second time? Okay, so Let's step it once again. So step. After we step, observe the changes that are happening here and record them, please. Instruction register. This thing is longer, okay, because I've minimized my screen. That's why you're seeing a short portion of it. But it holds all the instruction, MOV #10 R12. It also holds that same thing, MOV #10 R12, the same thing there. So you will enter it. And then the changes to your accumulator this time will be that the accumulator is now currently holding data 10 in register 12. So you write that accumulator is now holding 10. And after you do that, what will the instruction be? Move immediate value 10 to R12. That's all. Let's step it again. Time a call. So let's move fast. If it's good, we did all the fundamentals a long time ago. So now the third step executes this particular line of instruction. This thing is always standing on the next instruction, by the way. It's doing what the program counter wants. So this step here says add R07 to R12 and store it in R12. So R7 had 15, R12 had 10. We've added them together and they are stored in the destination operand, which is R12. You see that? 25. So then you are going to update your things accordingly. You will record all these values here, the ones that correspond to the particular things you are seeing here. And after you record them, your accumulator value now becomes what? 25 for Betrasher. And then what happened? Add the value stored, or add 15, sorry. Add 15 stored in register 7 or in R7 to 10 stored in R12 and store the value or store the answer in R12. You write that there. Let's move on to the next one. So we step again. Upon stepping, this time, new instruction says we are moving the data in R12 to R20. So if you come to R20, you see that it has now been updated to 25. It has copied the data in R12 and it has pasted it in R20. And then it says again that we step, it pushes the data into the RAM. And also, there is something interesting to note that after this push is done, that's when the stack pointer updates to 898. It means the stack has grown taller. So now we are pointing to the new top of the stack. It's no more 896. It's now 898. It has moved up by 2 bits. So it has been stored there. Let's proceed. And we hit the last instruction. So you write that here. Your instruction or the answer to that is going to be push the data stored in R20 to the RAM, or push it into the program stack for the RAM. That's what there is to it. And we step it one last time in the program, and then you record all that you can see there. It even gives you a CPU runtime and everything. It's like an actual CPU. Good. So that will be the execution phase for that. Remember the evidence that it required you to do. It says you show the program counter changes. So it doesn't tell you when exactly to show it. So it means you can come to this line here or this line here. You take a screenshot of this side and you can use an arrow to indicate the program counter where you edit the photo, right? At 6. And then you take another screenshot maybe after you run to this line. And then you take that screenshot, you use the arrow to point to it, showing that the program counter has changed from 6. Okay, that will be your evidence for that. And it says show evidence of the memory buffer register holding data. So you take a screenshot of the NDR is holding the current instruction, or which is data stored in a particular address, by the way. It takes that you show that image. You show the memory address register holding an address. You put it there. You show the instruction register holding the instruction. You take a picture of it. So you just take pictures of them, use an arrow to indicate IR on any, MAR on any, MDR on any. I hope you are following and understand. Bear with me. We have to move fast. So there is no right. And then the accumulator updating, for the updation of the accumulator, you cannot show anything unless maybe you take a picture of the register on this side, right? And then you give a little explanation on it, or you give an actual explanation to say the accumulator is not shown explicitly inside the central processing unit operating system simulator. However, it is implied, or its work is implied through the job of the registers, the destination operands of the registers. Let's move on. Critical analysis questions. When is the memory address register loaded relative to instruction register? So the memory address register is loaded before, okay, the instruction register. The memory address register is loaded before the instruction register, because we have to load the memory address so that we take what is inside the memory address and give it to the instruction register, and then it will know what to use that instruction data for to execute the program. So when is it loaded? It is loaded before the instruction register. This information might be false, so I beg you to verify, okay? Check if it is loaded before or after. My brain might be confused, but then I think it is before. Does the accumulator change during fetch? So does the accumulator change during fetch? The answer is no. When you're fetching data, it does not change. When you're fetching data, it does not change. Fetching means we go to a memory address and we read data. It does not change. Explain using observed data. So you can observe here that when we're fetching an instruction, for example, when we're fetching a random instruction such as the push instruction, there was no change done to the accumulator. The reason why I'm not using the move instruction is during a single cycle, there is a fetch, there is a decode, there is an execute, right? The fetching and decode and execute, unlike in the Littleman computer, have been done in a single step. So I cannot separately tell you when fetching was done, decoding was done, or execution was done. If I try to use this to explain to you, you'll be like, but the data value changed to 15. So what do you mean that the data didn't change? That's because the fetching, decoding, and execution have all been done at the same time. So it didn't really change during fetch. It's only changed during execute when the program instruction was implemented. So keep it in mind. You explain that during the fetch stage, the program, the accumulator's value does not change because during this time, the program will read an instruction from memory or read a data value from memory and does not write it or move it to the program counter. And you can go further to say that it is during execution that happens. Which register holds operand data during memory read? So when we are reading from memory, which one holds the operand data? So the operand data is held here, okay? The opcode data is held in the instruction register. The operand data is held in the memory data register. All right. Sorry, did I just say memory data register? Memory address register, okay? So the operand is held here, the opcode is held here in the instruction register, whereas the operand is held in the memory address register. Let's keep going. So go and use these to answer questions. I hope you're taking notes because this is the last session we'll do on this. What will happen if the program counter does not increment automatically? So if the program counter does not increment automatically, the program is going to stop running. The guide said to move from here to here. So if it's not incremented automatically, the program will come to a stop, right? So the program is going to halt due to the fact that the program counter is not giving us a new address to update to. Identity and one example of computer organization from your observation. So architecture architecture has to do with things that are physical to the programmer. Organization has to do with how things are arranged to execute. You can use the transfer then instruction orderliness. So the control transfer can be an architecture thing, and then the orderliness of instruction can be used to talk for instance organization thing. Okay, the control transfer, how the program move from one point to another, one point to another, how it's built. You can look into it, okay? Or you can get creative with your answers. You can have AI suggest some to you, and etc. etc. We're running on science, so for the weighted answers, I believe AI can help you with that, right? So let's proceed. Perform Amdahl's law, performance and Amdahl's law, sorry. Assume instruction counts is 500. Central processing, cycles per instruction is 1.5. Clock rate is 2 gigahertz. Answer the following. Compute execution time. We've already looked at the formula for execution time, and then the formula is what? for instance, CPI times instruction count divided by, for instance, the rates in this, the clock rates in this case is 2 gigahertz. So you're just going to do 1.5 times 500 divided by 2, and then you're going to get your answer for that. So you state the formula, Amdahl's law. It says you are supposed to calculate what compute execution time. Execution time is equal to CPI times, right, in full if you want. So your compute execution time for that. Next one says, if, please, am I making myself clear with that one? Okay, bear with me, we have to move fast. But if you have questions, still ask anyway. It still helps in the long run. People, are we confused? If you are lost,
We are okay.
it's sad, but actually, okay. Thank you. Thank you for that affirmation, boss. In Miss Nancy's voice, you'll be fine, eh? You'll be fine. Let's move on. Now, next one says, if 40% of instructions are memory instructions and the memory speed improves by 2 times, compute speed up using Amdahl's law. So this one is just a formula thing, so you use the formula. The formula stated for this particular one, please, can someone help us with it? Someone help us with the formula, Amdahl's law formula. Hmm? You don't know? Okay, let me help you with that. I've forgotten what lies on top of it. Is it 1? But underneath it, there is, so we take all the values that we have been given and we take them into account. Okay, so it says if 40% of instructions are memory instructions and memory speed improves by 2 times, compute speed up using Amdahl's law. The formula is given by, let me just pull it from my file for you to have a look at it, okay? Because it's a little long, so but it's a simple one. You can keep it in mind. This is much similar to one of the formulas of what we call it, probability from statistics. Combines 2 parts of one thing. I think which binomial is it binomial probabilities? What is it called? The probability that takes the chances of it not happening and the chances of it happening and then multiplies them together. It subtracts 1 from 1. It subtracts 1 probability from 1 to get the other.
Why are you trying to give us PTSD?
Oh, sorry. Okay, see here. It's okay. Okay, it's right here. That's why. So let's see. Good. So the formula is 1 over 1 minus the fraction of change. Okay, this one is 40%. So 1 minus f going to be 1 minus 40%, or 1 minus 0.4, and that's going to give you 0.6, right? And then you add that to f divided by sm. The sm is what does it represent? The memory speed up. So how fast the memory has sped? According to the question, it was sped up by 2 times, right? So you do 1 divided by 1 minus the fraction of change plus the fraction of change, which will be 0.4, divided by the speed up, which is 2. And after you compute that, you get 1.25. This means that the memory speeds up by 1.25 times. And it says, explain why the total performance does not double. And let's see what that entails. So the single reason why it doesn't double is according to Amdahl's law. If some of the instructions are sped up, so if 40% of the instructions in memory are sped up by 2 times, this will mean that the remnant 60% will still be trying to move at the same speed at which they were moved. The fact that 40% has raised the speed doesn't necessarily mean that all of the CPU's speed has been accelerated. The only acceleration is happening with the 40% that are successfully running faster. But then the other 60% of instructions that are not running faster will still be lagging behind. Therefore, even though there will be an increase in the memory speed, it will not be up to 2 times. Up to 2 times will mean that the speed will double. But the speed is being backed by the the initial speed without the speed up. Therefore, it will not increase by 2 times. Rephrase that in the best way you can, okay? May the good Lord be with you. Explain why total performance does not double. That's what we just talked about. Identify the performance bottleneck observed in your simulation. So there is only one bottleneck that is inside the central processing unit operating system simulator, and it cannot be observed with your eyes, but just the knowledge in your mind can tell you that. We are aware that the CPU works very fast, right? And due to how fast the CPU works, it needs at every single time it has to fetch, decode, execute, fetch, decode, execute for every single line of code and instruction. For this reason, it has to be able to access memory space very fast and retrieve data. Registers are fast, but they are still not as fast as the CPU is intended to be. So for that reason, if we are retrieving data from registers, it makes the what do we call it, CPU slow, and that's why we have cache memory. And cache memory are also types of registers, but they are even faster and then they are closer to the CPU. So the bottleneck that we experience here is that retrieving data or fetching data from registers actually makes the CPU operations a little slower, or not even a little slower, makes it relatively slower than it should be. That's the bottleneck. Change input values and execute the program again. So we've come to the end of it. So we are going to change the instructions and then we compare the instruction counts. But even without changing, we can tell. It says we are only changing the input values. We are not changing the instructions. We are only changing the input values. So what would the instruction counts be? Now, if I change the input here from 15 to 4, and I change this one to 6, will that affect how many instructions I have here? Please answer me. If I change this to 4 and I change this to 6, will that affect the number of instructions I have here? Do you think it's well, yes or no?
No.
It won't, right? Exactly.
No,
Therefore,
it
the
won't.
instruction count stays exactly. So the answer to that question is that the instruction count stays the same. And the reason why it stays the same is that the changes were made to the data stored in the registers. However, the data or the instructions themselves were not in any way altered. Therefore, instruction count stays the same. It just says you should compare, so you say it stays the same. Then you check accumulator behavior. Now, accumulator behavior, on the other hand, will change because I said the destination addresses are now acting as the accumulators, right? If I change the data value here from 15 to 10, the memory address 7 is going to be updated with that value 10. To 10, right? Good, I said 10. So it is going to be updated with that value 10. Now, what will happen is register 12, even if we don't change it, let's say we don't change register 12, it stays the same. Now, the data value that will be combined from 15 and then which we have changed to 10, the one that will be added to the 10 in register 12 will now update the register 12 towards 20. So then the register 12's initial value didn't change, but its final value has now changed towards 20. This means that the accumulator behavior has changed. And this is because when you read and write data into memory, if they are numeral inputs, they will be held in the accumulator. And for that reason, this will change the PC behavior. And what about the program counter jumps? The program counter jumps will not change either. This is because we didn't use any branch instructions, so it will execute in the same order which it did. And I think if you add a branch instruction to your own, then you should include that the program counter jump at a particular level. But since we didn't do that, you don't do it. And now you explain the differences. So over here, you wrote instruction counts. Instruction counts remain the same. Accumulator behavior changed. That's the comparison. PC increment sequentially just as before. And the difference will be that the accumulator behavior, everything else stayed the same, but AC changed because data values were being changed, and then the destination address were now being updated with the new data values. I think we have come to the end of it. We have come to the end of it. Did you like that? So far so good. I wish you good luck, okay, and all that. But if you want to understand this better, we will provide the YouTube links. I hate to do that. I'll not lie to you. I'm not a hypocrite. I hate to give you something that people have paid for, because even you will attest to the fact that it's not fair. Aside that, I want my money too. So I don't see why I should give it to you. I'll not even give it to you. Let's proceed. So you must submit completed tables typed, not handwritten. Not handwritten. There should be photos too. And not handwritten photos, sorry. So you take a snapshot and all the required screenshots that were mentioned. And it also says a 3 to 5 minute screen recording explaining your execution trace. So all the programs you executed, since it's a 3 to 5 minutes video, you move. Yes, sir.
Please,
Yeah.
what about the calculation part? Can you show it on paper and put it in a word?
See, it says completed tables, all required screenshots. It didn't really say anything about, yeah, it says not handwritten photos. But it was referring to the table, so I don't know about the calculation though. I don't know. Yeah, you know what? I think you might be able to do that. You might be, but Charlie, to be safe, what type here? I bet your time, Kakra, but it's just 2 questions. That's a calculation type questions. Just to be safe, type it.
Okay, sir.
Lecturers are on a mission. All right, let's
Brother,
move on.
please,
Yes, sir.
do you think per this submission requirement that you are reading now, do you think the LMCs also will require the 3 minutes to 5 minutes recording explaining your
You see-
traces, or it's just for the
You see,
it's just for the CPU OS?
look at something here. When you come to the marking rubrics, it says correct LMC tracing. So yes, conceptual explanation. So it says it has taken that into account. I don't know if that is referring to the text written one or it is referring to the explanation itself. But here's what I think. Perhaps your 3 to 5 minutes video should be explaining what you have on your paper. So do you see the traces that you did? They have been taken a screenshot and they have been put on this. It could be that. Or maybe it could mean that actually open your LMC and then start explaining that, okay, program counter increments memory address register, and then blah, blah, increment this and blah, 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 blah. Maybe that's what it means. But as you have said, that is a little too much for a 3 to 5 minutes recording. So you just do a recording that shows that you know what you're talking about. You see that? So you can decide to focus on LMC, or you can decide to focus on the central processing unit operating system simulator. I think either one works. It says conceptual explanation. They didn't really specify where. Okay, so I think either one works. Just show that you know what you're doing, okay? And then, that's all. So performance calculations, you explain them too. So you explain your calculations, by the way. It's over calculation, you might not explain, the formula no say, okay, the formula, 1, 2, 3, 4, you say whatever, then you move. And then they should all be in a type PDF reports that combines all the parts. And it says that it's based, forget all of that sense. No fabricated traces or reused recordings, zeros and all that and all that. So yeah, we've come to the end of our session for today. Even though I moved fast, I'd like to believe that I helped you in some way. Thank you for participating. Even though I'm not happy about the fact that you didn't pay, but at least I'm glad that we are all making it right. That is also an achievement. Have a great night, people. Do you have a question to ask before I end the session?
Yeah, yes, Prince. Please, it's about the reporting side. So that one, which side are we going?
Reporting side. Which reporting side, man?
He's talking
Yeah,
about
please,
the reading report.
or the reading report. Oh, the reading report, you go to your Stallings manual, read chapter 1.1 to 1.4. After reading it, make notes on what you have observed from those sides. He did not specify how exactly the note should be, but it should be like your understanding of what you have read, put in text form, and then you submit the PDF. So that one has nothing to do with this particular one. It is the Stallings manual. So if you go to Sakai, you open the Stallings manual, you download it. Read chapter 1.1 to 1.4. Make inferences from your reading. Then use that to create what you like, ideas from what you have understood or whatever in a PDF format. So Word first to PDF and then you upload it to Sakai. Okay, so please, is that clear?
Yes, brother. Yes.
Okay, we're done. All right, so we are done. Okay. If there are no further questions.
Hello, Prince.
Okay, I'm listening. Yes,
Are
sir.
you
I
Am I a
wanted
teacher or a
to know.
student? I'm a student like you, a student who wants your money.
Yeah, I wanted to know
I'm
if you would submit these same Word documents, like we edit the things here and put the answers here, or we do it separately elsewhere.
Yeah, you can do it that way. He does not say this is mine, right? And I just put the answers because his was a Word document, so he said it's also. I just put my data right underneath his questions where it's supposed to be. So I
Yeah.
believe you can do same. It's convenient to the table and all that. Actually, I think I copied the data into a Word document, yes, but basically it's the same thing. It's the same thing.
So the video recordings and everything can come inside here. Just here.
On the video recordings. Now, if you are using the web version, I've noticed that. So Joshua, what you were asking, if you are using the web version, like what I am using now, the video recordings cannot be added as embedded files. They have to be links. So it means a link to an online video. But if you are using the web offline version, I think you can actually add a video as an object. So I don't know, please, is any of you on PC right now? Let's try doing that so that we will know, and then yes, we are able to train the account, because currently I think the screen recording is what some of us are left with to do. So please, is anybody on PC and has web the offline app, any version, at least 2016 and above? Obi any. So can you anyhow you see a 365? Mr. Jed, I know you have money. Stop playing with us.
Freeman.
Okay. Yeah, it's true, but Freeman. Okay, listen to how I think it should be done. If you go to your, if you are using the offline version and it is quite recent, if you go to insert and then the options here, you are going to see insert text objects or text and objects or something. Select objects, and once you select objects, select like to upload a video file, or select a file to upload, and then go and select that particular video file. If you see any option that talks about it being a link, try not to take it, okay? Else it will try to embed it as a link instead of an actual video. Or alternatively, you can just copy and paste. Okay, if it is able to support the selection and adding of a text object in video format, then it should be able to copy and then paste it too. Okay, so that's one way to go about it. And there are other software that will allow you to do it, but you will not be able to store it in Word document format. You will store it as an ODT file. So if you have the ODT file, you can convert that ODT file into, I think LibreOffice will do that for you. You convert that ODT file maybe into a PDF, but I don't know whether or not the video will still stay. I've never tried that before. I mean, when we were in Form 1, do you remember Dingo showed us a lesson, and then there was a video about AI inside it. I think that one, there was a PowerPoint slide.
Yes, I
You know,
remember.
you remember, yes. So I think it is possible to do, but I don't know whether it will stay when we convert it into a PDF. Maybe you can do it as a PowerPoint, convert to PDF or something. I'll try a few things, and if I get any updates, I'll put them on the pages. Okay. For now, it's goodbye. It's late. Get some sleep, people. Get some rest, Ali. Tomorrow, the lectures will catch you again and molest your brains. Go and sleep and prepare for that. Have a great night. Mr. BT, your hand is up.
Yeah, good evening.
Okay, Madam BT, good evening.
Please, it's about the video. I don't know whether it's only on the last question, which is the part C.
You do not know whether the video is only on the question C.
Yeah, is it the last question or all the questions where the program is being used?
All right. If you read it carefully, it says that your execution trace. So he doesn't specify if it's the CPU or the LMC. So I think either one will be fine. Just show that you know what you are doing. Because 3 to 5 minutes is not much. If you can do all in 3 to 5, that's fine. And he also says that your calculations, which are in part C. So this leads me to believe that maybe if you do just part C with a CPU or a simulator, it will be fine.
Okay. Thank
Yeah.
you.
Yeah. Yes, Mr. Dennis Ayensu.
Yeah, please, I just joined. I was offline for some time. So can I get the recording?
Yeah, there's always yet you. That's it. Okay, we'll try to make the recording available. Okay, we'll try. But you guys, you realize that you're not paying for this, eh? Hey, Nipa that is it. Yeah. Yes, Mr. Boyne.
Mr. President, it's not like we don't want to join. No, if we should adjust the money small for us to, so that everyone is willing to join, but the payment is very huge. When
Oh, but
you give one,
Mr. Boyne. But
yeah,
Mr. Boyne, see, look at this. We are teaching all 6 courses at 270 cedis. Now, if you look at it to you, you might say it's a lot, but we know that in other departments, there are people who run courses for a course like just UGRC 110, and then they take 150 cedis per month for that UGRC 110, a single course. So if you are getting all 6 courses, right, and you can see how we are guiding you through now, there's an assignment, so, and we are walking you through it. I should be asleep by now because me and my and then I just skip, and I have continued all the way till this time. Don't you think appreciating the effort with some 270 cedis is worth it? You just tell me honestly. I know that it might be hard to pay, but we have payment plans. So you speak to the people in the finance department, they will handle it. We all face these financial constraints every now and then, it's true. But Charlie, we can't go like this forever. I know you're bigger than that money. I know, pa, you cry, you know. So please, if you would like for the payment plan to be done for you, don't worry. You can come, you meet our minister in charge of finance, finance minister, and he is going to help you. Okay, he's going to help you. If you are able to provide these resources, we'll also be able to buy better material and then use to tutor you. Eh? You must get it to 270 receipts, yes, eh? I'm not saying you will receipt, but actually, I know some people who said if they had met our courses earlier, perhaps they might not, not that they will not, you are not God, they might not have had to reset some courses. Sometimes you are in the distance department, who need be out you see that you have nobody to go to. These are the only ways that sometimes you can help yourself. But then again, Charlie, you each month with their own, but think about it, okay, 270 cedis. It's worth it. Mr. AF, Mr. Jacob Frank, or Jacob Frank, Jacob Frank, if you wanted to speak, you may speak. So that we say approve in the media.
Oh no, I'm okay, Prince. I'm okay.
Oh, okay, all right.
You're okay, right? I have. So please, the report today. You said where can I get it?
So go to Sakai, go to DCIT 207, go to lessons, go to is it lesson materials or resources or something? And then amongst this, you will see Stallings, whatever. Download it and then read chapter 1 to 1.4 and then use it for your report, okay?
Okay. So 1 to 1.4,
yes,
right?
That's right, sir.
All right.
Yes,
Thank you,
please.
boss.
Yes, sir. Answer bless.
Yeah, please, I want to ask of the report writing. Are you going to write in a report form? Then we should read reports.
Yes, so maybe yes. That's what that one is. It's a reading report, right? So perhaps if you do the format, a report format, hey, I should have done that too, Charlie. Yeah, probably.
So that means it's reports like reports writing.
No. Not like a report, like where you're recounting like an event, that type of reports. But this one is like when you read what you have discovered from it or what you have understood from it, put it in speech form or put it in this one text form and submit to him. I do not know if it has to strictly follow report format, but yeah, I think it's worth a try. There is no harm in doing that, honestly.
Okay.
Yeah. So yeah, no. South Havana,
Hi, Hi. With the video reports that you said is on Sakai, I've gone there, but then I can't see anything.
Are you talking about the assignment itself or the file that you have to read?
The file that we are supposed to read.
Okay, so you will put it on the platforms right now, and they will be there. Okay, yeah. Okay.
Thank you.
Right. This our lecturer, so he doesn't like when we do these things. So you see, last time when Mr. Evans was trying to help, he was talking plenty. So we should be careful about how we do these things. All right, so have a great night, everybody. We'll be anchored actually. Yabre. Everybody go and sleep. Go straight to bed, though. Don't go anywhere. Goodbye. Mr. Manasi. Yeah. Manasi, the financial guy. Okay, you when you see any of our communiques, reach out and then we'll direct you to the financial guy. He's a very chill guy, actually. He gets sense why he will help you. Goodbye, everyone.